Let's talk about mathematical induction for the last part of our introduction to semantics for our standard first-order theory. Mathematical induction is a particular form of induction. Induction in general allows us to generalize from specific instances to either generalizations or predictions. So if you think about induction and the way it works in natural sciences, that's what you're thinking about. In any case, in our context, general induction of the sort we use in science isn't going to be relevant. So in science, perhaps you see a whole bunch of white swans. Every swan you've seen so far has been white. So swan number 1 was white through however many swans you saw. And from that, you make a prediction or a generalization. The next swan I see will white. The next swan I see will be white. Or the next swan, or all swans are white maybe. In this case, that's what we are going to do. We are going to start with some properties of specific numbers, and then we're going to generalize. Every number has a particular feature. So we're looking for a property phi, and if we can say a couple of things about this property, we'll be able to generalize. Every number has this property. What are these properties, this property phi? What is it that they have to have? Two things. We start with, this is called the base case. 0 has phi. Sometimes instead of 0 we'll use 1. The first natural number has this property, but in any case we have to establish that in the base case the property holds. Second, we're going to make a general claim for any n. If n has phi, then so does n plus 1. If both of those clauses hold, then we're going to be able to say every natural number has phi. So the first clause is the base case, the second is the inductive case. If you're interested, if you're highly skeptical, maybe no arguments for anything count as good enough arguments for them. But if you're less than highly skeptical, maybe you're suitably skeptical, you'll want an argument for this form of argument. So here's the idea. Suppose you've proved that both clauses are true. You then wonder why this makes phi a property of every number. So assume that it's not true. Assume there is a number without the property in question. Call that number m. There can't be such a number though, since by m applications of the inductive clause, we'll reach m and show that it too has phi, because we will have shown successively that it holds for each number after 0 and m number of times. By the time we get there, we'll have shown that the preceding number to m it holds for, and the inductive clause tells us that if we've shown it for one number, we can show it for the successor number, and that successor number is m. And so we will have shown that it too has phi. So there can't be such an m, which is to say there can't be a number lacking the feature in question. That's the argument for it. Let's look at two examples. One example is a faulty example. We'll get to that next. Here's a simple, good example. It actually illustrates both proof techniques that we'll be using in this part of the course, in the metatheory part of the course. We're just going to prove that every whole number is either even or odd. Now, the first thing we do is exploit a definition of even and odd. And remember, one of our proof techniques is proof by definitions, by appeal to explicit definitions. So, for every whole number, our hypothesis is, for every whole number n, there is an m such that n equals 2m, or n equals 2m plus 1. It's not written down here, but the first is our definition of what it is for a number to be an even number. For an even number is for it to be identical to some number multiplied by 2. For n to be an odd number is for it to be equal to some number multiplied by 2 and 1 added to it. In any case, those are our explicit definitions, which we're going to use in this proof. So first we're going to consider the base case, the case where n equals 0. For the base case, m can also be 0, since 0 equals 2 times 0. So in the base case, n is even. So in the base case, n is either even or odd because it's even. Now consider the inductive case. Assume that there is such an m for n, and our job is to show that it also holds for n plus 1. So n is either even or odd. We get to assume that. If it's even, then there's a number m such that n equals 2 to the m, and then n plus 1 will be equal to 2m plus 1. So if n is even, n plus 1 will be odd by the definition of odd above. So suppose n is odd. Then there's an m, this is our explicit definition again. Then there's an m such that n equals 2m plus 1. If so, n plus 1 will be the odd number plus 1, and that's 2 times m plus 1, which makes n plus 1 even by the definition of even above, since there's a number such that n is equal to 2 times it. So our inductive case is proved. Notice what we did was we proved a base case, we then proved an inductive case, and then by mathematical induction, we draw our conclusion. Since both the base and inductive cases are established, it turns out that the property in question is one that every number has. Now to a faulty example, a case where superficially the structure of the argument is exactly like in the good case that we talked about previously, but where there's a mistake in the reasoning. It's not a structural mistake because this is going to follow the same structure as mathematical induction in general, but just because it follows that structure doesn't mean all of the premises are true. So what we're going to do is prove that if every horse is just a single unicolored horse, then every horse is exactly the same color as every other horse. So if you want to think about this, just rule out examples like paint horses and pintos and multicolored horses of any sort. Just let them all be either brown or red or chestnut or black or white or whatever. Every horse is just one color. So let's assume every horse is of one color. Then the claim is, if that's true, we can prove by mathematical induction that every horse is the same color as every other horse. So start with the base case. Here we're going to prove it by the size of the set in question. So one of the tricks in applying mathematical induction is you sometimes have to figure out what numerical thing you're going to be applying mathematical induction to. And sometimes it's straightforward, it's about numbers, so you use numbers. Other times it's not about numbers, so you have to talk about something else. The size of a set is a natural way to go. When we get to linguistic items, maybe we can talk about the complexity of a formula in terms of how many connectives it's got. Notice again, we have to do something before applying mathematical induction in order to talk about numbers. So here we're going to talk about the size of a set. How many horses are there in a set? Well, take the base case. The base case is where you have a set of no horses in it at all. So trivially, it's a set with horses all of the same color. The only way you don't get horses of the same color is where you have at least two horses that have different colors. So the base case is trivial. In the inductive case, assume that every set of n horses is uniformly of a single color, and show that every set of n plus 1 will also be uniformly of a single color. So how are we going to do that? Well, let's assume that it's false of n plus 1. If so, we're going to argue that it has to be false of n as well. So notice you've got a set of horses. And we're assuming that n plus 1 has different colored horses in it. But remember, we've already assumed that if the size is n, they're all the same color. So suppose n is 4. Then every set that has 4 horses in it will be horses of the same color. If you want, let B stand for brown or bay if you prefer. I don't care what you want to call it. Now we're going to assume, yeah, but that doesn't mean that you can't have a set of 5 where 4 of them are bay horses and one's a palomino. So we're going to assume that for sets of 5, it's false that they're all of the same color, even though for sets of 4, they aren't different colored at all, okay? So, what's the problem? Is there an inconsistency here? Yes, there is. If you start out with a set, if you're assuming all sets of 4 horses are of the same color, then you can't have different colors for sets of 5. Why? Because sets of 4 are any possible subsets of sets of 5. So you can generate, if you have a set like this, you can generate a set of 4 by dropping any member you want from the set of 5. Well, one way to do it leaves you with a set of 4 same-colored horses. Drop the palomino. But notice you could drop that one. Now you have a set of 4 that aren't all of the same color. But remember, for establishing the inductive case, we got to start out by assuming something. We get to assume that every set of n horses is uniformly of a single color. Then we looked at the consequent of the conditional for the inductive clause, and we said, assume that it's false of n plus 1. So we are making two assumptions. One is all sets with 4 horses in them are uniformly of a single color, but it's not true that all sets of 5 are uniformly of a single color. But under this assumption, the falsity of this assumption generates a contradiction. So if we assume this, then where n is 4 and n plus 1 is 5, we get a contradiction. And notice as you keep going up, the same thing is going to happen no matter which larger value for n you pick. So if you have let n be 7, and n plus 1 is 8. So you assume all sets with 7 horses in them are the same color. And then you assume that for the 8-membered set, there's one weird colored horse in there. But you can generate a set of 7 just by dropping any of those members. And 7 of the members, if you drop them, you end up with a set of 7 that violates the first assumption. So if every set of n horses is uniformly of a single color, then every set of n plus 1 is also uniformly of a single color. That is the inductive clause. So just as in the last case, we've established both the base case and the inductive case, so we generalize. All horses are the same color if every horse is just a single colored horse. You know that this proof is a bad proof, so the question is, what's wrong with it? Feel free to email me if you wish. There's another form of induction, sometimes referred to as strong induction. The difference between weak induction, ordinary mathematical induction, and strong induction is what you're proving. So with ordinary induction, we proved a base case, and then the inductive case that we proved said if it holds for n, it holds for n plus 1, excuse me. For strong induction, we similarly have a base case. You prove that 0 has the property in question. And then the inductive case looks slightly different. You assume that the property in question is possessed by every n minus 1 greater than 0. And then you show that it holds for n as well. So instead of saying if it holds for n, it holds for n plus 1, here you say if it holds for every n minus 1, it also holds for n, regardless of the value of n. And then you generalize on that. There is no logical difference between ordinary induction, the mathematical induction that we went through with the examples, and strong induction. So you can use either form. It doesn't really matter. In general, we will be using mathematical induction rather than strong induction, but I think there's a couple of proofs in the Cider book that rely on strong induction. In any case, that's enough on induction. So I've let you wait long enough. What's wrong with a proof about horses of the same color? The trick is, go back to the slide. The trick is in the inductive clause. The inductive clause requires us to prove that if it holds for n, it holds for n plus 1. And notice I started with the number 4 for n, and then went forward from there. Think about the smaller numbers, though. What about where n is 0? Well, 0, it was trivially true that all sets of size 0 have horses of the same color, and it's also trivially true that all sets with exactly one horse in them will be sets of horses all of the same color. So both for 0 and 1 we get trivial results about horses being of the same color or not being of the same color. But think about the move from 1 to 2. Let n be 1. The argument that I gave you was go to 2. So you've got a set, let n be 1, so let's say you've got a palomino in that set. And trivially, that's a set that has horses all of the same color, because there's only one, and that's its color. But then the argument I gave you was, let's assume that n plus 1, it's not true. So we're going to put a bay horse together with the palomino, and now we have a set of 2, and that set is a set that doesn't have horses of the same color in it. Now, the way I argued you could generate a contradiction here, when we talked about 4 and 5 and 7 and 8 and that sort of thing, was this. I said, well, if you've got multicolored horses at n plus 1, you can generate a contradiction for the first assumption, that every set of size n has horses all of the same color in it. But notice that argument won't work here when we had 5 and 4 for the relevant numbers. If all sets of size 4 were of the same color, then all sets of size 5 have to be of the same color, because you can drop one of them and violate the assumption about what happened with 4. But notice here, no such violation occurs. It doesn't matter which of the horses you drop, you're going to end up with a singleton set, and it will have horses all of the same color in it. So, what's wrong with this proof? What's wrong is where n equals 1 and n plus 1 equals 2, there is no contradiction to be had between assuming that it holds for n but doesn't hold for n plus 1. So, as expected, there is something wrong with that proof, but structurally, it has precisely the same form as every other case of mathematical induction. The lesson is you have to think about the truth of the premises being claimed. And in this case, the inductive clause had a faulty proof on its behalf. It relied on using larger numbers than the initial ones.